Okay, my friends, I am going to have a wonderful, wonderful time. This is the Office of Legacy Management, STEM, Commitment to Stewardship. Radiation and you. Well, what is radiation? All it is energy in motion, and they're going to explain it. This is the U.S. Department of Energy. They are the ones that control energy. I am going to debate with them on this video because they're going to try to explain the atom. And I say they do not understand the atom. I know, pretty arrogant, huh? Okay, so how can I be so arrogant as to say that the Department of Energy doesn't understand radiation and the atom, and I do? Well, here's why. Because this is nothing more than light from a red laser. Light is light. Red laser is the same speed as regular light. It doesn't matter. This is that light of the red laser accelerating. Anybody that has any, all you have to do is be able to see. You can obviously it's accelerating. It's just like a jet engine, a jet fighter taking off and accelerating and breaking the speed of sound. We're breaking the speed of light, literally breaking the speed of light. And here it concusses. And what does it concuss and show up at that point? It shows its particle nature, its true colors. And that's what they are. Black and white. And what are they? One of them is dark matter. The black is dark matter. The white is what we always considered was the glowy electron part. But they have a dark matter part to them as well. And CERN knows this. They've seen them break apart from the protons. They take these gigantic protons and they smash them together and all kinds of bits fly off. And they see these, which is the muon neutrino, the black ball. They see the white ball, and then they see the showers. This is exactly what I just showed you. So they see them, but they don't realize, because they just know that they came out of a proton. Where do they come from in the proton? The proton is made of the exact same particles light is made of, exact same particles electrons are made of. There's only one particle, well, there's two particles, there's a black and a white. That's the smallest particles that exist that I can find, and I think I have found them, and CERN cannot, and Fermilab cannot, and neither can the Department of Energy, because they don't even understand how the atom is constructed. Okay, my friends, I don't want to be insulting, but it's going to sound insulting. I cannot help it. Here it is, Understanding Atoms. This is from the U.S. Department of Energy. And I'm going to tell you right now, they do not understand atoms. Not at all. All right, this is very, very simple to understand. This is the current Bohr model where they got one gigantic proton. This is a hydrogen. One gigantic proton and one tiny little electron. And then they don't even consider the weight of the electron is so small. Here's the real model, is they're dipoles. It's not just a big positive core. It's dark matter surrounded by the white matter. I'm going to show you, and I can show you all these things. I don't have to guess at them like they're guessing. Okay, I am going to be a little combative and challenging because they won't stand up for themselves. Here they're going to make these statements, and I am going to show you that these statements are not correct. And then I expect to hear from the U.S. Department of Energy or someone from CERN or Fermilab or somebody. But they have refused to engage because I have them over a barrel. They are just literally lost, and they're the ones that are in charge of energy. Stunning. Okay, like I said, this is going to be a little challenging, a little combative. I say they don't understand atoms. I do. Let's hear what they have to say. The U.S. Department of Energy.
Like the building blocks of the universe, because they form the basis of all things that surround us, which is called matter. There are three main parts of an atom: protons, neutrons, and electrons. These are characterized by their electrical charge. Protons have a positive charge and are found in the nucleus or in the center of the atom. Neutrons are also found in the nucleus, but they are neutral and have no charge. Electrons have a negative charge and orbit the nucleus.
Okay, let's talk about that. That is the Bohr model. And here's what it looks like. This is hydrogen, which is the smallest of all of the elements. And supposedly it has one proton, which to them was just one big positive. and one tiny little negative, which is so small, it's only 0.000544 atomic mass units. The proton is 1 atomic mass unit. That's how they calculate atomic mass units, by protons. Now, I say that is not true at all. That proton itself is not one big ball like that. That proton is this ball. And this ball is 1,839 electrons. Let's look at Roger's model. Bohr model, she's a no more. That's a gone thing. This is what the real, and they know this because they can smash the protons into little bits and pieces and see all these particles. So they know the proton is not just one big ball. It can break into these particles, and they call them neutrinos. And they have a muon neutrino, electron neutrino, and I will show you those. So the real hydrogen atom is one of these balls of particles, and every particle is an electron. Every electron consists of 2 bits. One of them is the electron neutrino, the other one is the muon neutrino. Now, so and they're dipoles. So this is a dipole. This dark core is so attractive that it wants another electron to come into it. But these electron pushers, they push away. That's why they coat, because they don't want to be next to each other. They'll always go to the outside. So any more electrons want to come in, if it fills up that shell around that dark matter, it says, no, we're good. You can stay out there, but that's it. That's what's called quantum. And there'll be a distance out there that this electron can come to, but that's it. It can't get any closer. And if you look up tractor beam magnets on YouTube, you're going to find out it's really cool. They put a positive core and a bunch of negative surrounding it, and then the negative comes up, bang, and it sticks right out just like this. It's exactly identical. All right, so this is quantum. And they know that there is not just protons. Neutrons are only one electron bigger, and they know that too. It's exactly the amount of one electron bigger than a proton is a neutron. It's amazing. And then they have these little tiny electrons. Well, the electrons are only these little bits. All right? So this is wrong. They don't understand the atom at all. Let's go a little further.
Sort of like our Earth orbiting around the sun.
The
number of protons in an atom's nucleus determines the element, what the matter actually is. For example, the element hydrogen has 1 proton. Oxygen in the air we breathe has 8 protons. Copper, like what is used to coat pennies, has 29 protons. Most atoms are what we call stable because they have the right number, or ratio, of protons to neutrons in the nucleus. However, when the
all right, let's talk about stable atoms. All right, why are they stable? And they say they have the right number. The right number, why? What number is the right number, and why is it the right number? Explain that to me. I can explain it. It's because there's so many tiny particles, and there's some resonance frequency hum in the background that shakes these until they lock in. And I can show you that in the salt table experiments. I've shown all these things over and over and over and over. The salt table experiment literally shows the smallest orbitals, which only have one little core, and then they go into the rule of 8 when you get up to here. I've shown all this stuff. So what they're talking about is just not realistic at all.
proton to neutron ratio is not right in atoms, we call those atoms unstable, or radioactive. Radiation is the release of energy from the unstable nucleus of an atom as it struggles with being out of balance. That energy travels in the form of waves or particles.
All right, let's talk about that. Waves or particles. When they're talking about nuclear decay, they're usually talking about huge chunks of matter. And when they decay, they throw off big chunks. They throw off chunks like this. Well, light is way down at this range. Light can't hurt you. I mean, it can burn your eyeballs and so forth, and it can actually burn you a little bit. Light can, yeah, absolutely. But not like these chunks. Chunks like this, they'll just tear your cells apart. They'll just destroy you because they're like hand grenades coming from gigantic particles. I started with light. Light is light. It's the smallest particle there is. One of these is 1839 of the particles I'm working with, which is light. All right, so it's a whole different, well, actually there's two particles that make up the light, but 1839 electrons make up one proton. So when you get up into the range of these big heavy things, you got hundreds of thousands of actual particles there. And they just spit off all over the place. And if you get in the way of them, you're going to get injured. Okay, my friends, I don't want this to sound terribly arrogant, and it will sound terribly arrogant, because I'm going to tell you right now, the Department of Energy doesn't understand the atoms. They don't understand them. Ionizing radiation, they're talking about radiation. Radiation is nothing more than light, and it's the speed of light, faster and faster and faster, hurts you. It's ionizing radiation. It's light so fast that it knocks off other light particles and creates what they call ions, and they can damage you. But down here in the radio waves, microwaves, infrared, visible light, partially into the ultraviolet, you're okay. We can live in that. They just illuminate you. They give you a little sunburn every now and then or whatever. But once you get up here, they actually create changes in the atomic structure. Think of it that way. These just sort of jiggle things around. These smash things and break particles. That's the difference. Now, we're going to get into radiation, and this is the Department of Energy and what they think atoms are made of. And I'm going to show you they don't know. All right, so this is light from a pulsed red laser. Not supposed to go any faster than that. That's it. Einstein says you can't accelerate it. Well, you certainly can accelerate it. And there it is accelerating. And how did we do that? CERN and the rest of them claimed that they had this accidentally happen and created matter by bumping particles together. Well, we created the division of the light. The black and the white particles were separated. Here they are attached. There they are right there. That's what they should be. That's what they should look like. Let me get these out of the way. They're radiating up there. Radiation is everywhere. Now, there's the black and white balls. That is the light. That is the actual particle that's coming out of that light wave accelerating. And you don't see that particle until just before it concusses. And I'll show you that, because here's the progression of the particle. Where is it? There we go. Can you see way back over here? You don't really see anything coming through. It starts to show up a little bit. You can see it black and white. And then it starts to show up pretty obvious. And it gets glowier and glowier. And then it explodes at the venturi. And the black and the white literally come apart. That is fission. And then what happens is you end up with fusion. This is the fission right here. And that's because there's a slit here that's so tiny that only the white squishy part can get through and the black cannot. So we have fission here, and we could do this all day long. This is not something that's uncontrollable. This is actually very controllable. But you have to have the right engineering and so forth to create this exact situation. The black ones come around, which is the muon neutrinos, and the white ones go into the spray, electron shower. And the only reason they can do that is because the white ones are squishy and mushy and fluidy. The black ones are just like bowling balls. They are heavy as hell, and they have no ability to react other than to just attract the white ones back. They don't do anything else. And they cannot crush either. These can. These can crush, they can expand. They're expanding because this one at the bottom is coming forward and impacting with the light that's in the air, or the particles that are in the air. Because every gas isn't made of all the same things that the light is made of. They're all made of dipole electrons. So it's push to shove. This one's pushing against those. This one's pushing real hard. These aren't, they just got to get out of the way. So they're not getting excited like this one. And this will fill up and flip to the back, and this one will come to the front, and then that'll flip. That's a muon wobble. So I say they don't understand, because these particles are inside of protons. When they smash the protons, they see these same particles. So they came out of the protons. It's not like they're hidden. It's just they don't understand them. All right, so the current Bohr model, it just doesn't work. It never did work. It's actually kind of crazy. Now, I showed you the photons, and I say that one photon is comprised of 2 electrons, and each one of them is like a bar magnet. Now, a single electron will burn into you. It will fuse to things. It is static, it is lightning, it is electricity, and all it wants to do is find ground, find the easiest part to get to ground, which is earth ground. When you have a bunch of extra electrons on you, static it's called, and you touch a water pipe or something for the ground, it snaps right off of you. Those are electrons. They're not photons. Photons are basically a neutral bit of material. It's 2 electrons together. They bounce off of you. They hit and they bounce off of the other electrons they bump into. Push to shove. And they push hard, it shoves back not quite as hard. So you're going to have all these different colors, and that's the reason for all the colors, is because of the push and the shove back. I have the same amount of energy hitting everywhere here, but you see I have all kind of different colors. Why? Why? The reason is the thing that it's hitting has its own pushback. All right, then they're not the same. That's why some of them are green, some of them are red and blue. Anyway, I say that the particles that they're going to be talking about, which is protons, neutrons, and electrons, are all made of what we consider to be electrons. They're dipoles. And they never knew the dipole. They always thought electron was just a negative. Nobody's known about the muon because that's the dark matter. Everything there is, half of it is dark matter. Only the half that's dark matter is the half that has the weight. That's where almost all the weight is. Electrons, they don't seem to have any real serious weight, but boy, I'll tell you, they can burn like hell. And you can see that in an atomic bomb very simply. The first thing that happens is everything just combusts, and then boom, the big black ones come. The electrons are on the outside of everything, so they go first, and they just light up everything, and then the black ones come right after them, and then they knock everything down. Shown it a bazillion times. Okay, here's the Department of Energy again. We crushed the fields by forcing them into that little venturi. We crushed them. We didn't collide them. We crushed them. This is what they did in photons to try to do this. And they just, I know they have to be understanding what we've been doing. I've been trying to keep after these people for years. The primary finding is that they found pairs of electrons and positrons, the black and the white particles. Matter and antimatter. It's not matter and antimatter, it's dark matter and white matter. And they say it can be created directly by colliding very energetic photons. We force them together. They're quantum packets of light. Well, I agree with that. They are quantum packets of light, the photons. Now, then they say this conversion of energetic light into matter is from Einstein's E equals mc squared. That is not a correct equation. All right, C is you could see C is not a set speed. It's just not. You can go faster, you go slower. It states that energy and matter are interchangeable. Well, energy is matter. Right? Matter is made of energy. Sometimes it's in a state of where it doesn't do anything. It's just sitting there, but it's energy. Okay, this is the Department of Energy again. Not correct. Collision of light produce matter. No, that's not true. The collision of light produces pieces of that light and shows it as matter, and they say antimatter and matter. Well, it's not. It's the white and the black ball, the muon neutrino, electron neutrino. They think it just comes out of nowhere. I'm seriously, they just think it just automatically happens. Produces this matter from nothingness. I mean, literally from nothing they think they can get matter. The truth of the thing is, the primary finding is that pairs of electrons and positrons, I showed you the black and white particles, those are what they're talking about. The particles of matter and antimatter, that's not really true. They're not really antimatter, it's matter and energetic matter. Can be created directly by colliding very energetic photons. You can't create that. You can split them, yes, but you're not creating anything. They say it can be created, and I mean, I'm serious. They think it just creates automatically, and that's what they're talking about. This could lead to the reason we have a Big Bang, because a bangness would make all this matter create by itself. It's just amazing how they can distort reality. Absolutely amazing. You see, it's all based on E equals mc squared. Well, C, it can go to all kind of different speeds. I showed that. All right, here's the red and green coming through the Venturi exact same time. They're both accelerating. And the green impacts way out here because it's so much more powerful. Now, there's no question that that light is accelerating. It's impossible to deny that. And to not allow this to be spoken about when they show the exact same thing that we are doing here. And that's fission, that's fusion. This is cold. This is an increase of energy that's exponential. They say it's 207 times an increase in energy if you can do what we did, which was to separate the particles. All right, way back there's almost no energy at all. Here it's just unbelievably powerful. And you could see it if you just take a second and think about it. Just look at it. Back here there's nothing. You can't see anything back there. There's no energy whatsoever because we don't have an energetic particle yet. We just have light. Light is not energetic enough to do any of this. And now we accelerated it. Now you see it, no question whatsoever, that particle, which is a particle, and it has a magnetic field surrounding it. So it's a magnetic wave, and now the particle itself is exceeding the magnetic wave. It's pulling ahead of it. Here, the concussion and the radiation is so enormous that it's coming backwards, and we can see all of these light particles which are coming this way. You can't see them because there's not enough energy. Only at the exact impact spot are we having enough energetic particle to be able to pick it up with these CMOS. And you can see this stuff is no problem whatsoever. And this has been since 2014 we've been able to do this and see these particles. These pictures come from right around that time frame. The green is identical to the red. There's no difference whatsoever, only it's a lot more powerful. It's spinning a lot faster. But it's the same particle coming out in the same trail like that. Only the red just doesn't have the oomph. The red is sort of lumbers across here and then just begins to show up and splits here. And, oh, I got so many things I could show you here. It's just amazing. But this is the basic deal. The light comes in, the light accelerates, the light splits, and as it comes out here, this is raw energy. This is where we should be able to harvest a ton of energy just by putting a solar panel in here. And I have the, oh, I have it around here. It is. This is what I want to talk to them about at Brookhaven and Fermilab and all these places. They're supposed to be doing this exotic. As far as I'm concerned, we split that particle. I could show you, and it's black and white splits. And if that's the case, we're supposed to be getting 207 times more energy. Just look it up. That's what they say. I'm not saying it, they say it. But you can see the increase in energy is just exponential. From here, there's nothing. Here, it's just like an atomic bomb, and it literally is a subatomic explosion. Fission, fusion. We get in between the fusing part, and that can run anything you want until it fuses back to the black side. and we can tap off a tiny little bit, keep the laser running, we're exceeding what we're using many, many, many times. So this is like literally free energy. You don't have to plug into any grid. You can just plug anything you want into this and carry it around, go into woods with them, go into third world countries, anything you want. This is the savior of this earth if we're going to save the earth. And as far as I can see, nobody cares enough to even look at it. For 6 years at least, I've been begging them to look at this, and nobody will look at it. That's why I'm being so combative and challenging today. I wouldn't let anybody speak to me the way I speak to these people. They just run away and hide. I would confront that, and I'd say, oh, wait a minute, sir, Roger, you're not right, and here's why you're not right. And your pictures are wrong because of this, this, and that. No, they just say, you're an idiot, go away. And I'm done with that stuff. Okay, so once again, Department of Energy, U.S. government, Department of Energy, running trying to figure out how all these atoms work. And I want to be spoken to about it because this is not a proton. This is a proton. It's made of all kinds of little dipole electrons. Now I'm going to just let them play their spiel, and I will interrupt as I feel that they're wrong, and there's going to be a lot of interruptions.
To heal us when we're sick, explore space, and power the lights in our homes through electricity produced by nuclear power plants. To better understand radiation, let's start with atoms. Atoms are like the building blocks of the universe because they form the basis of all things that surround us, which is called matter.
Everything is made of atoms, but atoms are made of electron dipoles.
There are three main parts of an atom. Protons.
Protons are made of 1,839 electrons. Neutrons have just one more electron, and if you weigh it out, that's exactly what it weighs, one more electron than a proton. So you have protons, neutrons, and then you have the electrons. The electrons make up all these other parts.
Neutrons and electrons. These are characterized by their electrical charge. Protons have a positive charge and are found in the nucleus or in the center of the atom.
They are dipoles. These are dipoles. The only reason a neutron is what they call neutral is because it has an even number. Protons have an odd number. All right, that means they want to take one more on or give one up.
Neutrons are also found in the nucleus, but they are neutral and have no charge. Electrons have a negative charge and orbit the nucleus, sort of like our Earth orbiting around the Sun. The number of protons in an atom's nucleus determines the element, what the matter actually is. For example, the element hydrogen has 1 proton. Oxygen in the air we breathe has 8 protons. Copper, like what is used to coat pennies, has 29 protons. Most atoms are what we call stable because they have the right number, or ratio, of protons to neutrons in the nucleus.
All right, I'm going to show you how that actually is established. When they say it's the right ratio, why? Why is it the right ratio? Why? There's going to be a reason that they lock in at these different numbers. And the reason is resonance, frequency, vibration. All you got to do is talk to my friend Nikola Tesla. Okay, this is Bruspup. Fabulous. Amazing resonance experiments. They're going to take salt, which is a polar molecule, just like these are polar particles, and they're going to put it on a frequency table that they're going to vibrate with just electronic frequency, and it will, and you'll see the salt molecules form patterns. All right, so here we go. Here's Nikola Tesla. Now watch the frequencies. This is the plate. And all they are doing is shooting electricity in back and forth like this to shake that plate. That's what they're doing. They're doing that frequency. Now at a very low frequency, you're going to have the first group of the periodic table. And that means it only has one core. Then once you get to the next layers, you end up with the rule of 8. So here it goes down here where all you have is hydrogen or helium. All right, you see that? That's the tiniest orbital. That's the lowest orbital core, and all it can have is 1 or 2 or 3 or possibly 4 electrons surrounding that particular one thing. Now, once you go up into the next range, you're going to hit the rule of 8. Watch. See it lock in only at that frequency. You have to be at the right frequency. Now, in between the other, look, it's just all buzzy, and all of a sudden, bam, it locks in at 1033. And now you have, whoops, you have obviously seen the rule of 8 there. All right, let's go back up here. Here's the rule of 8. All right, now, that is going to be one of your most basic rule of 8 elements. They all have 8 valence electrons when they are stable in their most, what they call noble. So that they don't want to give up or take any more. They're just perfect. They say, oh, no, don't come in, and we're not letting any go. We're perfect. We're stable. We are a noble gas primarily. Now, you go up through, in other words, this has a very, probably that would be neon. All right, there's your 8 electrons surrounding the core. That would be probably neon. And then as they go up bigger and bigger and bigger, you just get more and more electrons. You see? And they lock in at more and more, but they every time they buzz all around, and then bam, they lock in. And they're these elegant patterns. Look at these patterns. Amazing. Now, once you get way out to the very end here, you end up with particles that are so big that there's just too many bits and pieces to hold on, and they decay semi-quickly. And then there's other ones right in between all these different ones that are called isotopes. So they don't really have the right number, and they are only have a certain amount of normal life to them before they decay and become something else. Those are isotopes. It's just a matter of how many particles you have in the nucleus. Some are isotopes, some of them are very stable. Oxygen has all kinds of different states, and all your transition metals have these different oxidation states, and they can grab onto all other these different particles and carry them around through your body. This is what your blood is made out of, transition metals. A lot of thinking to do. All right, so this is why they become stable. And again, some of them don't have exactly the right number. It's not like you got one gigantic proton here and the neutrons and everything's just exactly right. Some of these protons might not even have the 1839. They might have 1835 or 42. It doesn't. They're not going to be exactly stable. That's what isotopes are. And even hydrogen has a zillion different isotopes. Lithium has, I think, 21 isotopes. Hold on a second. All right, I told you, isotopes are nothing more than not having quite enough electrons or having too many electrons. And they're not going to stay because they want to become stable. So they will eventually decay or change to become stable. Look at this list of isotopes. I said 21, I was wrong. There's only 13, but that's a hell of a lot of different types of lithium. You'd say lithium is lithium. No, it's not. There's lithium, this one, all the way down. And they have all kinds of different characteristics and stability. The only ones that are stable, really, is the 6 and 7. Lithium 6 and lithium 7. Those are the stable ones. The rest of them have half-lives that are 9 years, 5 years. Some of them have like seconds. 8.7 milliseconds. You know, anyway. How could you do that with these one big gigantic particles like they just talked about from the Department of Energy? They don't understand. These particles are made of these particles. Okay, I hope I made that pretty clear. So we got all kinds of different isotopes, and they're not just 3 protons and 3 neutrons. Absolutely not.
However, when the proton to neutron ratio is not right in atoms, we call those atoms unstable or radioactive. Radiation is the release of energy from the unstable nucleus of an atom as it struggles with being out of balance. That energy travels in the form of waves or particles. There are 4 types of ionizing radiation. This high energy is released from an atom as either an alpha particle, beta particle, neutron particle, or gamma ray. Alpha radiation is created when an atom's nucleus releases or ejects 2 protons and
Have you seen that before? The particle that he just showed you, there it is right there. That's the one I'm showing you. They see them. I don't know why they just don't fess up and say, yeah, guess what? Roger was showing us the right stuff. All right, so there it is right there.
Protons and 2 neutrons as a single particle. You can visualize alpha radiation.
Now they're saying it's 2 protons and 2 neutrons. That may be, but I have 2 neutrinos of the muon and 2 of the neutrinos of the electrons. So I don't know if they really understand what they're seeing. Because they're talking still down in the, well, let's make sure I'm right here. I don't want to make a mistake. All right, here we go.
2 neutrons as a single particle. You can visualize alpha radiation like being a big beach ball. This particle is the largest of the 3 radiation particles and only travels an inch or so in the air. It can be stopped by a sheet of paper or plastic.
All right, which is basically light. That's the photon.
Beta radiation occurs when a neutron, which has no charge, is transformed into a proton and an electron inside the nucleus.
All right. This is hilarious. The neutron, which I'm saying is just 1 extra electron, they say it transforms itself by spitting out an electron. Well, how could it do that if it wasn't made of electrons? Let's listen to this again. All right, here we go. Beta radiation,
which has no charge, is transformed into a proton and an electron inside.
A neutron transforms itself into a proton and an electron. That's because it's made of 1840 electrons, and now one of them goes over here, and 1839 of them are over here.
Inside the nucleus, and then the electron is released from the atom as a beta particle. You can visualize beta radiation like a ping pong ball. It's fast and small, much smaller than the alpha particle, and it travels a lot further, up to several feet in the air, and can be stopped by a thin sheet of metal or protective clothing.
All right, that is really the somewhere in the photon area, down in the little particles. I showed you the black and the white, and I'm not sure where that particular particle is.
Neutron radiation is mainly created when a uranium or plutonium atom fissions.
All right, when they talk about fission here, they're talking about some big, gigantic particle, and it breaks like that. That's their fission. And that hits you, you're in trouble. When we do the fission of light, we're down, way down into 1839 particles inside of one of those tiny particles. So these are, the particles we have are not going to kill you like these will. This is deadly fission.
Or splits when creating energy for electricity. Let's visualize neutron radiation as a softball, bigger and stronger than a beta ping pong ball. Neutron radiation can travel hundreds of feet in the air, but can be blocked by materials like concrete or water.
All right, that is the dark matter. That's the dark matter. Dark matter is just heavy as hell. And it's the dark matter that's attached to the little white particle I showed you before. Basically, it's this. When this goes off in an atomic bomb, the white particle is always on the outside. It goes first, and it burns things. Then these come and smash into concrete and everything else and blow them all away. And that's the only way you can block that particular black particle, the big heavy-duty one. I'll show you in the nuclear bomb in a minute. Okay, so that's the one that...
Gamma radiation is a ray of energy, or a wave of energy, so not a particle at all like the other forms of radiation. If alpha radiation is like a beach ball, beta a ping pong ball, and neutron a softball, then gamma radiation is not a ball at all. Rather, it's more like a light beam emitted.
All right, that is what I'm going to show you that burns before the black ball comes and explodes.
By a flashlight. This high energy wave requires several inches of lead, concrete, or steel to be stopped.
See, it will burn, you watch.
So you now have a better understanding.
All right, well, I hope you have a better understanding, but not the understanding that they gave you, the understanding that I gave you. Now let me show you how the atomic bomb proves what I'm talking about. All right, this is one I did a while back on. It's called Einstein's Peer Review by Roger Spur, and he did not do well. A lot of push. So this one here is the heavy bowling ball particle. This is like a flamethrower particle. Watch what happens here at the house. Now I have this running a little slow on the playback so we can watch it. Here goes. I got the sound off. Now, it's going to be the blast goes off. Okay. All right, now, I just want to explain this a little better than maybe I did before. At this point right now, the atomic bomb has gone off. And what we are seeing is the white particles coming. They're the first ones to hit. They have no mass to them to speak of. They're just burners. Watch it burn this thing. All right, here we go. Okay, so here we are. Boom. It's just burning. I'm going to stop it just so you can see. It's just combusting. Not a single thing has blown back yet. Watch. It's just burning, 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 burning. And all of a sudden the black ones will hit. See, it's just burning. And it's literally burnt almost everything that's burnable. And all of a sudden, pow, comes the black ones. Boom. All right, so these are the different particles they were talking about before. Don't forget, my claim is that the white ones surround everything always. The dark matter will go and snuggle right up to itself in the center. It seems to be fine doing that. So when it goes off, the white ones go off first. They are burners. There's no real impact to them, although they burn like hell. And then these come next and hit. Now, what will happen next is that the black core is still back where the bomb went off. And now it says, hey, I need some of you white guys to come back here. And they turn around and come back. Watch. You would not expect that. You would expect the blast to just keep going. No, they turn right around and come back. Boom, there's the black ones. Now watch what happens. It'll start to come back. See, it will turn around and come back this way. See the dust and everything's coming back. Why did that happen? That happened because back where the... All right, well, I explained it. Back where the bomb went off is still dark matter now. Dark matter can't exist on its own. It's everything, that's gravity. And you're seeing gravity in the air, gravity pulling the stuff back. Okay, so these kids are learning from the Department of Energy, and I say the Department of Energy needs to discuss the things that I have shown.
Understanding of what radiation is and how it contributes to our daily lives. Remember, radiation is energy in motion that is all around us, all the time. It also occurs in many different forms and plays a part of the Office of Legacy Management's mission to protect human health and the environment.
This is another thing they need to talk to me about, is mud fossils. I mean, I'm telling you, there is a condition that exists now that says, you say what I tell you to say or I will fail you in your life. So you have to say what they tell you to say. And they refuse to engage with people that have evidence, such as me. It's not really acceptable. You know, this is supposed to be a democracy where everybody has freedom of speech. I have freedom of suppression of speech. And that is actually academic fraud. These people are academics. And that is academic fraud, is suppression of valid information. I think this has got to stop. I don't know, academic fraud, deliberate suppression of relevant evidence or data. I've shown it for 6 years minimum to everybody that's been doing any of this kind of work and have not had anybody respond or except for being nasty. So I don't see this as being, I see this as a problem. I see this as academic fraud. Now, if it was just academic fraud, that would be one thing. But if we can get free energy and they refuse to, this is 6 years ago, I was showing this, saying, please, please, not a single word. This is, the earth is going to hell in a handbasket, and nobody cares enough to stand up. And the reason they won't stand up is because of peer review. You stand up, they destroy you. Trust me, I wouldn't be able to sweep floors in any of the academic institutions speaking the way I speak, because I am honest. Now, once again, I know it sounds terribly arrogant, but I take courses all the time. I've gone to the University of Geneva and all of them. And these, they follow what I do, so they send me these things. You should look into this. These are all free. I haven't paid a penny to anybody for any of this stuff. National Research, Nuclear University of Colorado, electrodynamics, field effects, optical engineering. These are all the things I do. And I've taken all kinds of courses already in this, so they just keep up with me. You know, they keep sending me these things. You know, these are designed, well, here's what it said, recommendations for you. Now, this is, I've done this my whole life, so this is not something that's new for me. And I knew back when I was first got out of the Army, I was in Nike Hercules missiles in the Army. I was going to go into electronics, and I did go into electronics, but I was going to go into physics, and I just found it was nonsense, absolute nonsense. Back then, this is 50 years ago, two types of intermolecular forces, dipole, dipoles. That's all there is push to shove, dipole against dipole. Bohr model, totally wrong. Rutherford atom was wrong. The transfer of energy is from light to atomic vapor, as I showed you or will show you. I am not new at this, but I still am. I'm still doing it. I do it every day, as everybody knows who knows me. This is what I do. I'm sorry, it's a compulsion. I cannot help myself. All right, watch this. This is Yale. And again, I go to all these schools. You don't have to pay for this. They have all kinds of courses, but you don't get any credit for it, but you get to learn. Now, I learned that they're not right. Listen to, and they admit they don't know what's going on. Listen to this.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal.
He's just going to tell them, well, listen to him. Here's his goal as a teacher of quantum mechanics.
Right now, I'm the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So,
unfortunately, that's true. Because they have no clue about it. They're told, you say this, and if the student says what you told him to say, give him a good grade, and that means he can remember well. That's not really education in my book. When they refuse to engage with what I show as evidence, when they say we have no idea what's going on, and they refuse to even engage with evidence, not just a theory.